So good morning, this is lecture number 6 of Controle em Espaço de Estados. And remember that we have been speaking about the solution of the homogeneous equation x not equals to ax. And we came to the conclusion that when the matrix A has n independent eigenvalues, n independent eigenvectors, sorry, then you can write the state at time t as a sum of terms like this. So a constant that depends on the initial conditions times an eigenvector times the exponential of the corresponding eigenvalue multiplied by time. Okay, so in the case of a 2x2 system, you have two terms of this. Each term is called a mode. Okay? And we have seen that from this formula, we understand that the eigenvalues shape the way in which the system works. Shape the so-called phase portrait, that is to say, the evolution of the solutions or of the orbits of the state when time passes, the curves that the state follow in the state space, in this case in the state plane. Okay, and I told you that if you don't have n independent eigenvalues, n being the dimension of the state, then what happens is that you have some extra terms that are polynomials in t multiplied by the exponentials. But since the exponentials dominate the polynomials, the conclusions, for instance, about stability are the same. That is to say, for x to return to 0 from any initial condition, you have to ask that all the eigenvalues have a negative real part, so that these exponentials correspond to terms that are shrinking. Okay, then I told you that you should prepare yourself for the beginning of today's class by listening to Waterloo's ABBA, the music of the ABBA. Who has done that?
I've done that.
Okay, good. So you will receive a chocolate as a prize for that. So what do you know, Ricard? What do you know about Napoleon?
He was a French emperor and was defeated by Wellington in Waterloo.
Okay, so he was not French. He was from Corsica, but he was emperor of France. In that sense, he was a French. And what about the relations of Napoleon in Portugal? Do you know something?
3 invasions. That's all I know.
3 invasions. That's right. It's very hard. You see, I used to spend my holidays since I was a child, a little bit by chance because I have no familiar connections there, in a small village close to a place that became famous 3 years ago because of the fires. It's a small village close to Oliveira do Hospital, and it's close to the river Mondego. And the French in the third invasion passed the other side of the river. And these French were, we have a word in Portuguese that now it's not much used, but when I was young, it was very much used to say that someone is very bad. We call it marau. I think that marau comes from marauders. Marauders, or in French, maraudeurs, were some isolated troops that were spreading around the main army, and they were stealing everything, all the food and everything they could to supply the army. So some of these marauders came to this village in the third invasion, and everybody escaped away. But there was a lady who remained. She said, well, they're not going to do me any harm. And she stayed with her doctor, who was a little child. And when the French came, they immediately cut it, her throat. And then some French soldiers wanted to do the same to the child, and some other soldiers opposed. And while they were disputing about that, the peasants were hidden in the middle of the maize plants, meio do milho, and they called the child and she escaped away. Okay? And I still met great grandchildren of this child who escaped from the French. So it was really a terrible time of invasion. Portugal was robbed in many ways, and the population suffered tremendously because the peasants they could find anywhere, they were considered, especially in the third invasion, they were considered um, partisans. I mean, guerrillas, and they were immediately killed. And people were completely robbed out. What the French could not steal, they were destroying. It was a terrible thing. There are studies now. There are some scientific studies with statistics about what happens and the impact, not only during the invasion, but in the years to come on health and on the economy and so on. It was something quite nasty. So, as you said, Napoleon was defeated by Wellington in Waterloo. Okay, and my idea is that we model the Waterloo battle here using a state model. And what happens was this. Well, Wellington was leading an army that was a coalition. Actually, there were in the army of Wellington, people were speaking about 17 different languages. So you had people from everywhere. Most of the most important part were British. And the French outnumbered this coalition. Okay, the French outnumbered this army of allies led by Wellington. And the fight started. It started late, at about 11 o'clock, because there was some rain the day before. And Napoleon was also not so energetic in starting the battle. So this is probably one of the reasons why he was defeated. And it was a very hard battle. You know? And there were another army of Prussians that were part of the Allied forces against Napoleon. But they were away. So Wellington called for them, and they were coming very fast. And there was a dramatic moment in which Wellington said, well, either the knight or Blucher must come, otherwise we are lost. Blucher was the general who was leading this Prussian army. And actually, Blucher came in the last moment, and he turned the tide of the battle, and the French were defeated in a complete way. Okay, so we have these two features. First, when the battle starts, you have more French than allies. Let's call it British to simplify things. And but then Blucher comes. Okay, so let me share my whiteboard so that we can think a little bit about these facts. Okay, now I start by a question. How do you model two armies? Using what is the state variables that you can, the simplest ones that you can use to model two armies?
The number of soldiers.
The number of soldiers. So you have two armies, and how many variables do you need?
Two.
Two. Okay, so we can say that a simplest model is to have a state in which x1 is, say, the number of French, and x2 is, say, the number of Allied troops. Okay. We could have a better model, say, dividing x1 into artillery and infantry and cavalry. But okay, let's be very simplistic and use this. So we need equations for x1 and x2. Okay, so what is the simplest equation that we can write for, say, x1 dot in terms of x1 and x2? Well, the simplest function is probably something like alpha plus beta x1 plus gamma x2. Now, this is a simple. Then we could add quadratic terms, but let's keep our model linear. So alpha, beta, and gamma. What about alpha? Do we need an alpha?
I don't think so,
Why not?
because the x1 dot is just the number of soldiers killed per second.
Yes, well, you don't have a creation of soldiers, so we don't have alpha. What about beta? Beta can be either positive or negative. For instance, a positive beta, would it make sense?
No, needs to be negative
Why?
because soldiers are not being created.
So if beta was positive, what would be the solution without any x2?
Exponential of
A growing exponential.
yes, yes.
So you don't create soldiers out of nothing. What about a negative beta? What does it mean?
It means the more soldiers there are, the more are dying.
Yes, they could die by natural causes, by their own. Okay, but since the battle lasts for 1 day, so we are going to neglect this mortality rate. Okay, so we call this. What about gamma? Should it be positive or negative?
Negative.
And
Why negative?
Because the French die more when there are more allies.
Okay, because the French die due to the number of allies, and we assume it's proportional to the number of enemy troops. So let's select gamma to be -1. Okay, I could select another number, but the conclusions would be qualitatively the same. So I simplified it. I just put minus x2. What about the equation for x2? What should it be?
we could say it's minus x1.
Minus x1, so it's symmetric with respect to that. Okay? So we have a state model, and this state model is something like x1 dot in matricial form, x2 dot equals to 0, minus 1, minus 1, 0, x1, x2. Everybody agrees? So this is a very simplified model. And we have some initial conditions, okay? So x1 of 0, I would say 3. x2 of 0, I would say 2. Multiply by 10,000 and you have 30,000 French and 20,000 allies. Actually, the numbers were about 2.5 these numbers. Okay, so you had about we had about, I think it was about 16,000 French, so twice, and 50,000 allies, something like that. Okay, but let's take 3 and 2, and when I say 3, it's 3 times 10,000. I'm using the as unit 10,000 soldiers. Okay, and I'm measuring the time as hours multiplied by 10. So 1 in time here means 10 hours. Okay, now let me do it like, okay, here. I have x1, I have x2, and I have 1, 2, 3, 2. We have an initial condition here. Where does it go? Okay, what happens when you start with this condition, which is 3, 2? Where do you go?
It is pointing -2, -3.
What? I could not understand you.
It is pointing -2, -3.
Okay, so that's right. So we use that. Probably we could find the phase portrait. I mean, something that tells you, of course, you only consider the situation in which x1 and x2 are positive. That's the only one that is meaningful. But in mathematical terms, you can consider full values, positive or negative, of x1 and x2. So my suggestion to see how the phase portrait is compute the eigenvalues and the eigenvectors. So can you do it? So I will give you some minutes, compute the eigenvalues and the eigenvectors, and try to sketch the phase portrait. Everybody understands? When you end up with the eigenvalues and eigenvectors, please raise your hand. If you want to ask me questions, you can do it. I will be listening to you. So, no answers?
I think
You think what?
it is a saddle point.
It's a saddle point. Okay. So what are the eigenvalues?
1 and -1.
Okay, so you agree with my computation here. What about the eigenvectors?
It's 1, 1 and 1 -1.
So according to my computation, for lambda 1 equals to 1, it should be v1 equals to 1 and then -1, and for lambda 2 equals to -1, it's v2 equals to 1, 1. Am I right?
Yes.
So let's place here the eigenvectors. So one is 1, 1. And the other is 1 minus 1. Okay, so you have, can you tell me how to plot how to plot the phase portrait?
Then we see the direction of the vectors by looking at the eigenvalues.
Okay, so I have two directions. One is related to this one, and the other was related to this one. Now, this diagonal, this one, am I approaching or am I going away? 1, 1.
I think you're approaching because the eigenvalue is negative.
1, 1, so you are approaching. Okay, so you go in this direction. And what about here? Again, approaching. And the other one? In the other direction defined by the other eigenvector?
You're going away.
So I'm going away from the origin. Now, if I start here, what happens? I go in this direction, but then with a movement towards the other one. So I do something like this. And if I'm here, I go in this direction and then going towards here. Okay? Everybody agrees? So suppose that I'm here at this point. Let's call it P1. Who wins the battle? Remember that x1 is the French, and x2 is the Allies. If I start at P1, who wins the battle?
X2,
X2, so the Allies. Why?
because it's the first to reach 0.
Okay, so x1 reaches 0, so you annihilate x1 and x2 wins. What about here? If you start here,
It's the opposite. If X2 wins because X2 reaches 0.
that's right. And when you have an initial condition, which is x1 equal to 3 and x2 equal to 2, where are you? In P1 or in P2?
In P2.
In P2. So you somewhere here, you are in a situation that if you do nothing, the French would win. Okay. That's very bad, because we are coming to the conclusion that Napoleon won the Battle of Waterloo. You agree?
Yes.
But something happened. What happened?
The support from the Prussians.
The support from the Prussians. Blucher is arriving. Okay. So how do you model that? So you start, let's use another color, say green. You start here, you go on evolving, and then what happens after a while? When the
X2
Prussians
suddenly increase.
Increase along which direction do you increase?
X2 increases.
X2 increases. So you will go to here. And then what happens?
And then it follows the model.
It follows the model. So you do something like that. You win the battle. Okay? Everybody agrees with this reasoning?
Yes.
Now, we have one problem. And the problem is, what is the latest time, assuming that you start counting the time from this point, what is the latest time for which Blucher is able to change who wins? Because you understand what is the problem? Can you explain me what is the problem? If Blucher comes too late, what happens? If Blucher comes, for instance, at this point here,
They already lost the battle
why?
because an
Well,
increase in x2 it doesn't make the number bigger than x1.
So it would be something like that, and it was still like this. So what is the condition? What is the condition? You are looking for a time in which, what is the condition on x2 and x1?
x1 plus alpha bigger than x2.
X1 is equal
I don't know, x2 plus alpha bigger than x1, something like that.
plus, and alpha is the number, is the force of Blucher. Let's call it 20,000 soldiers, so plus 2. Okay, so let me be more precise. X1 of some TS, switching time. You can also call it TB, Blucher time, is equal to x2 of TS plus 2. Okay? Now, in general, what is the expression for x1? For x, sorry, for x, the vector x. What is the expression? Remember the modal decomposition. It's K1
times the first eigenvector
V1
times exponential of minus
lambda 1
eigenvalue
lambda 1 is 1. Okay,
plus
so
K2
I
eigenvector
can
2
even do what you say. So we have K1, K1, V1 is 1 minus 1. Exponential of t plus K2. And then 1
yes,
exponential
and
of minus t.
minus t.
Okay. Now, so I know x1 and x2, and this gives me some equation verified by the time in which you can still do some change, and you will, if you are right at that time, you will, both armies would be annihilated. So it must be a little bit before. Okay, but let's compute this time, this limit time. So try to compute this equation. Try to solve this equation with respect to TS. Remember that you can compute K1 and K2. Because you know the initial condition. Okay, don't forget the initial condition. So let me clean a number of things here. First compute K1 and K2, and then apply the equation, the condition. Everybody agrees that this is the equation to compute K1 and K2? So just write the expression for the model decomposition for t equal to 0. And for t equal to 0, x of 0 is 3, 2, and the exponentials become 1. So you get this condition. Now you have to solve it. Okay, so K1, sorry, this is K1. K1 is 0.5 and K2 is 2.5. Now that TS, the maximum switching point,
Teacher,
yes,
can I say the
yes, the result, yes, yes, sure,
Yeah.
sure.
I found minus log of kappa 1
Minus log of
kappa 1.
K1.
Yes, K1.
The minus is something strange because minus the log is a positive number, so there should be some negative time. So probably you have something which is not correct.
I think because K1 is between 0
Okay, it's
and 1.
0.5. So log of log. So this is okay, okay.
Is positive.
So this is log minus log of 0.5, you're right. Yes, you're correct. So this is minus log or plus log of 1 divided by 0.5,
Yes.
which is log of 2.
Okay. Simple.
Okay, which is about 0.60, 0.7, 0.7, okay, 0.692, 69.3. Okay, that's right, that's correct, that's correct. So let me conclude here my computation. So x2 is minus 2.5 ETS minus okay minus 2.5 ETS. I have something. What was the value of K2 I had?
2.5.
K2. So this is wrong here. Sorry. So this is 2 and this is 0.5. So this is 2.5 and this is 0.5. So again, this is what minus 0.5 plus that term 2.5 ETS. So when I apply this condition, x1 of TS minus x2 of TS plus 2, so it should be 0.5 ETS plus 2.5 E of minus TS must be equal to minus 0.5 ETS plus 0.5 ETS plus 2. Now this and this cut, and these are the sum, so you have exponential of TS is equal to 2, and TS is equal to the logarithm of 2, which is about, okay? So if you measure the time in tens of hours, it would be 7 hours. Okay? Questions or discussion of this result? Okay, so this was a game with the Waterloo battle. You know that there is one thing called the Richardson theory on war, which is not so much different from this. Okay, this is an adaptation of that theory. The Richardson theory on war is a little bit different, but explores the same type of arguments. And it refers, well, there is a nice example on the First World War in a book on differential equations by a guy called Brown. Introduction to Differential Equations. The author is Brown. Okay, any question? So this is a good exercise to make you think about phase portraits and the way the state evolves. Remember that in some cases, we have these jumps due to sudden impulsive inputs. In this case, the impulsive input was a sudden arrival of an extra arm. This happens in other contexts, for instance, when you have impacts of a walking robot and so on. So this type of arguments appears in many important cases in control engineering. So let's go back to our slides. Now, we have this solution. This solution is quite important because it makes a link between the type of response you get and the eigenvalues and the eigenvectors. But you can also look at the solution of the homogeneous equation x dot equal to ax with some initial condition in a different way. And this different way is try to find a map between the state at time t0 and the state at time t. Okay, and this map is defined by a matrix. So you should find a matrix that obviously depends on t and t0, such that if you multiply the initial state by this matrix, you get the state at time t. Okay, this is the so-called transition matrix. In the case where A is a constant matrix, this is nothing more than the exponential matrix. Okay, so for us, the transition matrix will be the same as the exponential matrix because we are considering only time invariant systems. Okay, so A does not depend on time. If A would depend on time, then there would still be this map, but you could not compute it as the exponential of a matrix. Okay, so one problem is, how can I compute the exponential of the matrix? One possibility, at least in formal terms, is to write it as a series. Okay, so assume that the series of the exponential is still valid for matrices. Of course, you have to justify that. But if your assumption is correct, then you can compute this matrix, the transition matrix, as this series. This series has a name, is the so-called Piano-Baker series. Actually, this is a special case of the Piano-Baker series. Okay, and when A is time invariant, you only depend on the difference between t and t0, not individually on the value of t0 and t, but only on their difference, the elapsed time. Okay, now this is not so practical to compute. So let's see some other methods to compute the exponential of a matrix. Is there any idea to compute the exponential of a matrix? Remember that actually the exponential of a matrix solves the equation. So you can say x of t is the exponential of a t minus t0 times x of t0. So by observing that the transition matrix or the exponential matrix, that's the same for us, solves the equation, one idea to compute, to get a formula for the exponential of a matrix. You have any idea? Well, just solve the equation. Methods to solve the equation. How can you solve this equation? Well, there is one solution. There is one solution that you have just learned 2 slides ago. You know that xt is a linear combination of exponentials. Okay. So if you somehow express this k1 and k2 explicitly on the initial state, then you will probably get a solution. And it's possible. Okay. Later we are going to see how this can be done. Another way of solving this equation. How can you solve a linear differential equation? There is a method that all of you know. Laplace transform. Okay, you can solve it with the Laplace transform. So let's solve it with the Laplace transform. So apply the Laplace transform. Okay, and when you apply the Laplace transform, now you don't consider zero initial conditions, you consider general initial conditions. So the Laplace transform of x dot is sx minus x0. Okay, and you solve it with respect to x. You solve it with respect to x, and you get x equals to the inverse of si minus a times x0. Now, if you take the Laplace transform, x0 is a constant, so xt is the inverse Laplace transform of the inverse matrix si minus a multiplying x0. So the exponential can be computed using this formula. Is the inverse Laplace transform. Okay, this T refers to our Laplace transform. In Portuguese, transformada de Laplace. Okay, I should have used just one L. So you compute the inverse Laplace transform of Si minus A inverse, and you get the exponential of a matrix. As simple as that. Okay. Let's see one example. Suppose that you have this matrix 1, 1, 4, 1. So you start by computing Si minus A, and then you have to invert it using the formula for the adjoint matrix. Okay. So you have to compute the determinant, and you have to compute the adjoint matrix, and okay, you get this inverse of Si minus A. Now you have to invert each term of Si minus A inverted. So you expand the terms into simple fractions, and now you know this is a sum of exponentials, as well as, I mean, all the terms are exponentials of 3 and minus 1. So you can compute the inverse of this term, this term, this term, this term. The computations are done here. I won't do it here. Okay, so you end up with the exponential of the matrix using the Laplace transform. Any question? Okay. Then another method is the series. And another method is this. If you take a matrix such that of two depends on two arguments, such that when the arguments are equal, you just have the identity, then this matrix verifies this. It's like the differential equation, the homogeneous differential equation, but now you have a matrix here. Okay, and this matrix that verifies this property is the exponential of the matrix. So you can show that xt is a matrix that verifies these equations times the initial condition. You can think as this as solve your initial equation with n different initial conditions that are 1, 0, 0, 0, 1, 0, 1, 0, 0, that is to say the canonical initial conditions. 1, 0, 0, 0, 1, 0, 0, 0, 1, okay? And get the different solutions, and then pack these different solutions as the columns of this matrix phi. That's equivalent to write this matrix differential equation. Okay, so you can see that what you are doing is that the columns of the exponential of a matrix, they form a basis, and at each time t, you can compute xt by making a linear combination, a different linear combination of different basis vectors provided by the exponential of the matrix. Now, you can show, and you can look at the exercises, and there is an exercise with some hints. When you study this, you can do it by yourselves, that the determinant of the exponential of the matrix is the exponential of t minus t0 times the trace of A. What is the trace of A? It's written here, is the sum of the diagonal elements of A. And this is a scalar exponential, the ones that you know. And you know that the exponential, it's a real exponential of a real function. It never vanishes. So there is no value of t, there is no time t such that this exponential is 0. So the determinant is always different from 0. Actually, it's always positive. So this means that the exponential of the matrix is always invertible. Okay, it's always invertible. So in continuous time, let me go to the whiteboard. And clean everything. Okay, so you have time. Suppose that you have x dot equals to a x with some x of t0 is some x0. So you know that x of t is the exponential of a t minus t0 multiplies x0. Okay, or if you want, multiplies x of t0. Okay, so to go from time t0 to time t, you multiply by the exponential of a t minus t0. Now, suppose that you are at time t and go backwards. Okay, by that theorem, this exponential is invertible. So you can say that x of t0 is the inverse of the exponential times x of t. Okay, so you multiply by the exponential of t0 minus t. That's the inverse of that one. Okay, so the time is reversible. Continuous time is reversible. Now, suppose that you have now a discrete time model. X of k plus 1 equals to a x of k. Now, and you have some x of k0 given. What happens? X of 1 of k0 plus 1 is what? How can I compute it from x of k0? It's just a x of k0. Now, x of k0 plus 2 is what? In relation to x of k0. What shall I place here? No ideas?
A squared.
A squared, because x of k0 plus 2 is a x of k0 plus 1, and x of k0 plus 1 is a x of k0, so that's a squared. Okay, so in general, x of k0 plus, say, n is equal to, what shall I place here?
N.
N. Now, let me write it in a different way. X of k is equal to a x of k0. What shall I place here? It's a difference of indexes, so it's k minus k0, right? Just take n as the difference. Now, can I say can I say that x of k0 is equal to a x of k0 minus k x of k? So going backwards, can I say this? Let me put question mark here. Can I say this? For this to be true, what is the condition on a of k minus k0? What is the relation between a of k minus k0 and a of k0 minus k? What is the relation between these two matrices?
One is the inverse of the other.
One is the inverse of the other. So I'm assuming what?
The matrix is invertible.
The matrix is invertible, because if a product of matrices is invertible, all the matrices must be invertible, okay? So only if A minus 1 exists. It's very simple to find a matrix whose inverse does not exist. Okay, so in discrete time, time is not reversible, you see. And this is a major difference between the theory that you can make in continuous time, when you can always go backwards in time, recover the initial condition, whereas in discrete time, this is only possible for some classes of systems. Was it clear, the point? And what is the transition matrix in discrete time? What is the transition matrix in discrete time? Is the power. Okay, in continuous time is the exponential, but in continuous time is the exponential, but in discrete time is the power. Okay, and the exponential is always invertible, but the power is not always invertible. Okay, depends. Okay, can I go along? Okay. So another property that you have in continuous time is this so-called semi-group property that says that suppose that you are at time t0 and you jump to time t2, and the states are related by the exponential of t2 minus t0. Now, you are at time t0 and you jump to time t1, and the states are related by the exponential of t1 minus t0. And then you jump from time t1 to time t2, and these states are related by the exponential of t2 minus t1. And the state is the same. So you can say that phi, so the exponential of t2 minus t0 is the product of the exponentials of t1 minus t0 and t2 minus t1. Okay, this is a semi-group property. Okay? We won't be exploring this too much, but it's a quite important property for solving many problems. The proof is here. I won't do it. The inverse of the transition matrix, just reverse. It's obvious in the exponential now. So you work formally, but there is a proof here that does not depend on the fact that it is an exponential. So this is valid even for time varying systems. Okay, so you interchange t and t0 and you get the inverse. The exponential is a continuous function of time, so you can differentiate it with respect to time. And another thing that I would like to mention to you is when we have non-homogeneous systems. So we have now this time BU here. And if you don't have the BU, so this integral is not there, and you just say that xt is the exponential times the initial condition. Now, when you have u, you have this, it's a kind of convolution integral, okay? And the most obvious way of proving this formula is to, what is the most obvious way of proving this formula? Can you tell me? This formula is the solution of that differential equation. So how can I prove that something is the solution of this differential equation with given initial conditions?
Just derive the equation and check the equality.
The equality, okay. So you must have a valid equality, a true equality. And there is something extra, you must verify the initial condition. What happens to this formula when t is equal to t0? Say in the exponential, what you get? You get exponential of a, and then t equal to t0, so this becomes 0. So the exponential of a0 is the identity. So becomes xt equal to x0 plus, and now the integral collapses because you are computing the integral in just one point. So it verifies the initial condition. Okay. So to compute the derivative, you need the formula to differentiate this integral with respect to a parameter. In this case, it's this t parameter that appears as the upper limit of the integral, and appears also here in the exponential. Okay, so this is brute force. Then there are two other methods. One is by doing a change of variables, and there is a problem in the problem series. So what you do is you do a change of variables. In the new variables, the solution is very simple, and then you invert the change of variables. So that's a technique that you are already familiar with. So there is a problem which tells you which change of variables should you consider. And then there is the superposition principle. So break your U in strips and compute approximately the response to each of the strips, and then add everything. Okay, and you get this formula. It's a very elegant way also. I think there is no problem about that in the series, but it can be also done. Okay, so remember that the solution of the non-homogeneous equation, that is to say of the full equation with the input, can be obtained in this way. In many cases, I mean, no one is going to compute this integral, but it's very useful to know that you have this expression. Okay? Usually, if you have some problem and you want to compute xt, you do some numerical, use some numerical method to solve the equation. You don't go and compute integrals. But this is important because if you want to prove some properties or study some properties of the solution, you know that you can stick on this form. Any question? A final word. A final word is just 2 slides for discrete time systems. In that case, the state equation, you know, it's xk of +1 equals to axk. Okay, so no input. And the solution, we have seen it, is a power of the matrix A. And again, you have something like the variation of constants formula. So that's this formula for the solution of the non-homogeneous case. And so instead of an integral, now you get the summation. And this summation, if you compute it, suppose that you have 0 initial conditions. It says that x of k, it's a linear combination. It's a linear combination, you see, as these vectors b, ab, etc., up to a k minus 1b. And the coefficients of the linear combinations are the control input samples, u0, u1, etc. This formula is quite important, in particular for predictive control. And later we are going to speak a bit about it. So this is nothing more than iterating this equation. Okay? And you can see that if you write this summation, you get this thing here. But if you don't like the summation, compute a of k plus 2 as a function of x of 0 and u of 0, then u of 0 and u of 1, and so on. So go on considering upper values of k, and you will get this formula here by induction. Okay, so this is what I wanted to tell you about the basic state model. Any question? So we stop here. And we will see each other next Wednesday, isn't it? No, next Friday. Next Friday.